Okay, today we're going to cover our second conic section, which is the ellipse. But before we do, how about a little circle review? So looking at number 1, it says to determine the equation of a circle having a given center, 2 at -3, and passing through an additional point or solution point of 4, 1. So of course you could sketch that out to kind of see the radius there. The distance from the center to any point on the circle would give us the radius. And what do we need to write our equation? Well, we need h, k, and r. What do we have? Well, we definitely have h and k. So let's go ahead and put those in first. We put in our h at negative, or at x minus 2. The h is actually positive 2. And for the k, we have y minus k, so y minus a -3 looks like a positive 3 in the equation. So that's really the first step there, besides maybe graphing if you want to. When in doubt, sketch it out, can't hurt. The next thing I'm going to do is we're going to take the point. The solution point is a point that must indeed satisfy the equation. So we know it's going to work. We put in the 4 for x, we put in the 1 for y, and we get this. So think 4 minus 2 is 2, 2 squared is 4. 1 plus 3 is 4, 4 squared is 16. So 4 plus 16, I have a radius squared of 20. Now the radius itself is the square root of 20. So for graphing purposes, you may want to think, about that number as a decimal to check your graph. Or we might want to give the radical of 20, which is 2 root 5, because it's 4 times 5. So we could state the radius, but we really want 20 to write the equation, which is our ultimate goal for this question. So we want r squared, so just leave it as 20, that's perfect. And now we're going to go back to that first one we wrote, but I'm just going to replace the r squared with the actual value of 20. And that's it, that's the equation of the circle. All right, for number 2, what form is it in? It's in general form, and we need to get to standard form to see the radius and the center of our circle. So the first thing I'm going to do is I'm going to sort of collect my families together. So we have our x family and we have our y family. And of course that -4, that constant term, I'm going to add it over to the other side. Now notice I left some space here. And the space is for completing the square, which is what takes me basically from the general to the standard form. So now I'm just going to think about how do I complete this x family. Half of -2 is -1, but -1 squared would be +1. And I need to make sure I add that to both sides. In the y family, half of 4, the linear coefficient, is 2. 2 squared is 4. So I'm going to add that to both sides. Now I'm going to factor, kind of wrap up my families, factoring those perfect square trinomials, and combining the like terms on the other side. And there it is. I've got my center radius form. What's my center? 1, -2, and the radius is 3. You got it. All right, so just a quick little review of circles before we go into the ellipse. And today we have our ellipse. Actually, a circle can be thought of as a special case of the ellipse. So sometimes they do put those together. But here we see the different conic sections we talked about previously. And today our focus is going to be on the ellipse, which basically looks like an oval shape or an elongated circle. It doesn't have a consistent radius, so that's the big difference there. All right, let's take a look. So the definition of an ellipse is a little bit difficult to understand, but it says that it's the locus of all points in the plane such that the sum of distances from 2 fixed points called the foci is a constant. And we have, instead of a focus point, which we've heard of with parabolas, I think in Algebra 2, we have 2 of them here. And if I wanted to draw that perfect ellipse and really sort of demonstrate the definition, I would move from my center 2 equal spaces from my center. So as I move from my center, let's mark the center here as the origin. And then this point over here is one of my focus points. And this one over here is my other. Now, these distances from the center are equal, and in variable terms, we refer to that distance from the center to a focus as the C value. So there's the C value right there. That whole distance here from the center to a focus is C each way. So that idea, if I put my sort of like maybe a push pin or one of those brad clips and tie a string, and then I put my pencil where the moving point is and kind of rotate it around, I'll get that elliptical shape. And the idea of the definition is that piece of string, the total length of the string won't change. The total length of the string is actually always 2a, or the length of the major axis. So there are some really interesting properties to the ellipse, and I'll put those links on your Teams page. But basically, the focus point, if you've ever heard of a whispering gallery, maybe on a tour of the Capitol, I know that when we did that, they pointed it out to us. So if you stand at one spot, if you stand at one focus and whisper in a three-dimensional ellipsoid, the sound kind of travels and bounces to the other focus point as if you were standing right next door, and you can kind of hear everything. So it's got some really interesting properties to an ellipse. So if you're interested in that, you can watch those videos. I'll share them with you later. But today we're just going to look at the equations and some of the basics about sketching an ellipse, writing the equation of an ellipse in standard form and general form, and kind of just working backwards in some cases. So the C, again, you see over here is the focus points, or the foci, as they're called for the plural. We go A each way to give me the vertices. And we have this other dimension here, B, the semi-minor axis. And some people would call these the vertices, or some textbooks might refer to them as the co-vertices. Sort of co-workers. They're not quite the major vertices. So we see those there. And the ellipse can be situated horizontally, as in that first diagram and the second. And then the third diagram there, you see it's situated vertically. So its major axis is the longer axis, and that's going to determine the way it's situated. All right, let's go over the language of the ellipse. You don't get lost in this, and this is where you might want to stop and take some notes here. So the center is HK, and that's pretty true of all of our conic sections. We're going to keep using that same terminology. The major axis endpoints are A each way from the center along the major axis, or the way it's situated. And so the major axis has a length of 2a, and that would be the length of your string if you were actually doing that little trick to draw them. The foci are the two fixed points referred to in the definition. They're always C each way from the center, and they lie along the major axis. The minor axis is perpendicular to the major through the center HK, has a length of 2b, or b each way. So the value of b determines the minor axis. The value of A is sometimes called the semi-major, half the major, because we go A each way. And finally, the eccentricity, denoted with a lowercase e, not to be confused with Euler's number e, but the eccentricity of an ellipse is the ratio of C to A, and it's a decimal that helps us to clarify the shape of the ellipse. So it's always between 0 and 1. The closer it is to 0, the more circular our ellipse appears. And the closer it is to 1, the more elliptical in nature that the curve will appear. All right, so the standard form of an ellipse, A is always greater than B because A determines the major axis, remember. Semi-major is A, so it's A each way, or 2A for the major axis. So to denote a one form vertical versus horizontal, we say that the A is greater than B. So in this first case, the A is under the X, so that means that my major axis is horizontally situated. However, in the second case, I see that the B, or B squared to be precise, is the denominator of the X term. The A squared, which determines the way, is under the Y this time, which would mean that it's going to be situated vertically. So the A shows the way, and the A has to be bigger than B, so that gives you a clue as to what to do. All right, moving forward, A each way for vertices, B each way for the minor axis endpoints, and some might say co-vertices. They sort of determine the width of the ellipse. Now, this is a kind of unique relationship. It is a Pythagorean relationship. However, C is no longer the hypotenuse. If we think about it, C is a leg and B is a leg. A has traded places with C. It is the Pythagorean relationship for the ellipse. So just keep that in mind. A is the hypotenuse. So C squared is going to equal A squared minus B squared. So we're going to go C each way for our foci. From the center. Everything moves from the center. And of course, it's along the major axis. Perfect. Remember to pause and take notes when you need to. Whoops. I went back. Too far. Sorry. Let's just run through it. And here. All right, so we said C squared equals A squared minus B squared. Well, 25 minus 9 gives me 16. The square root of 16 is 4. So we have a C value of 4. And what that's going to let me do is from my center, I'm going to go up 4. And that's one focus point. And from my center, I'm going to go down 4. Now remember, it's along the major axis, so how did I know I need to go up and down again? Where was my A? It was under my Y, which tells me it's a vertical type. All right? And so if I had to give my focus points there, you can see them there, 0, -4, and 0, 4. So I like to say graph it first and then go back and kind of give it its coordinates. Yeah. Go back one more time there. Went a little too quickly through the conic app right here. So the conic app will give you the foci in decimal format. We do want exact value, but it's a great checking tool. So make sure you know how to find it sort of both ways. All right, our next ellipse type is given a clue. Would you know what to do? Sort of working backwards type of situation. What if I tell you that you have foci at 0, 1, and 4, 1, and your major axis is 6? So you have a major axis of 6, and you have your foci given. So the first thing I want you to do is just sketch it out. What do we know? Where can we go? Well, hopefully if you plot the point 0, 1, and 4, 1, you can see easily that the midpoint of those points would be at 2, 1. And 2, 1 would be my center. I also can see that it's horizontally situated because remember the foci will always lie upon the major axis. So now I really do know that C is 2, the distance from the center to each focus point. And I know the equation type. Notice I threw in my center here as my h and k. Do I know my a squared or my b squared yet? No. How do I know my a squared is under the x? Well, look at my sketch again. Remember, I'm horizontally situated. That tells me that my a is going to fit, my a squared is going to fit as a denominator to the x term. Okay, next, what else can I find? Well, I've kind of exhausted that first clue about the given foci, and now I'm going to move to my second clue, that major axis of 6. What does that tell me? Well, I know it's horizontal. If the major is 2a and 2a is 6, what does that tell me? Well, it tells me that a is 3, and a squared must be 9. So now I can pull that into my equation. The last thing to find is the b, and I don't have any other information. Do I have enough to find b? Yes, you do. You know a, and you know c, and you can call on the Pythagorean theorem in a roundabout way, remembering that c is just a leg, a is the hypotenuse now in this relationship. So we typically write c squared equals a squared minus b squared. Fill in what we know. What do we know? Well, we know c squared would be 4, because c was 2. We know that a squared is 9. And so I can see a negative 5 is negative b squared, so therefore 5 is b squared. One last time, go back and fill it in. And you got it. That's the equation of your ellipse, working backwards. All right, this next slide, we're just going to wrap it up. What if we're not working with standard form? What if we're working with that general form? Well, let's take a look. Sometimes they are given to us in the expanded form, which means that the x minus h squared has actually been squared and like terms have been combined, denominators have been cleared, and constant terms have been also combined. So this means that there's some work to do. In order for us to get it back into shape, we have to make sure we know how to complete the square. Now, here's this type of completing the square has a bit of added degree of difficulty because those lead coefficients will always need to be factored out of each individual family as they occur. So if I see something like 4x squared, I'm going to have to factor the 4 from just the x family. 9y squared, I'm going to have to take the 9 out of just the y family. So there's some partial factoring to be done, and then of course redistributing to kind of balance the scale. So be careful with this. Watch our way through it and make sure you take some notes here as to the process. So consider this first equation. The first question is, would you know if it's an ellipse or a circle? Well, it seems like it says ellipse, so it's probably an ellipse, but how would I tell? Well, the idea is if I'm looking at my squared terms, I see different coefficients right from the start. I have a 4 as a coefficient to the x family, and I have a 1y squared. So when I don't see the same coefficient in both places of my squared terms coefficient, I know it's not a circle. So that is really the key. Moving forward to get it into standard form, like we did with circles, we're going to group our like terms together, or our families, if you will. So I put the 4x squared plus 8x and the y squared with the minus 8y, and that negative 8 or minus 8 I've added to the other side as a constant term. Next up, I'm just going to factor out my lead coefficient in each family. And I'm going to leave a little space to complete the square. So in the x family, what's my lead coefficient, it's a 4. So I'm going to just take that 4 out. Dividing by 4, I change that middle term to a 2. So it's no longer an 8. It's a 2 because I factored the 4 away. Did I change anything in the y family? Nothing at all, because what's in front of the y term, the y squared term, is just a 1. So there's nothing really to factor there. All right. Now, completing the square, I'm going to take half of 2, the linear term's coefficient, which will be 1, and square it. And let's put it back in. Now this can get a little tricky. A lot of students will make a mistake here, so please note this next step. What did I just add to the equation on the left? Is it a 1? Not quite. There's a 4 knocking at the door. Do you see this 4 hanging out here? So I really added a 1, but I've factored a 4. So in value, I've added a 4 times 1, which is what I need to put in over here. 4 times 1 gives me 4. So redistribute your lead coefficient before you balance the other side. Now in the y family, there's not much to do. Half of negative 4 is negative 2. Negative 2 squared is positive 4. And I really do just have a positive 4 on both sides. Let's go ahead and wrap them up. Factor your perfect square trinomials. Now notice the 4 is still out there in front of the x. Combine your like terms on the other side. We get 16. And we're almost there. But we have to have it equal to 1. It's not done until it's equal to 1. So last but not least, we're going to divide through my constant to get it all equal to 1. And now simplify any coefficients here. So the 4 divides into the 16 right here. And that would leave me a 4. And finally, there's my answer in standard form. What type is it? It's a vertical type. The a squared is 16, the a is 4. Where's my center? Negative 1, positive 2. And what's my b value? My b is 2. So my a is 4 and my b is 2. And it is a vertical type. Okay? So there it is, the center, negative 1, 2. Vertices, which way are they going? Well, they're going 4 up and 4 down from negative 1, 2. So I'm going to think of it like adding, I'm going to add a 4 to this 2. And I'm going to subtract a 4 from that 2 to get my new vertices. So 2 plus 4 gave me the 6, and 2 minus 4 gave me the negative 2. But the x-coordinate is going to stay in line with the center. The vertices are just moving up and down. And of course, you could graph it first to see that slide. But because it's under, and you may even want to just write that underneath it, a is 4, that tells me it's going to be affecting the 2, the y-coordinate of the center. I'm going to add it and subtract it to the 2. On the other hand, if I wanted my co-vertices, I would do 2 each way because the b value would be 2. If my b is 2, which coordinate it's going to affect is the x-coordinate here. So it's negative 1 plus 2 and negative 1 minus 2 to get my minor axis endpoints or co-vertices. So when I have negative 1 minus 2, I get that negative 3. And when I have negative 1 plus 2, I get positive 1. And notice in this case, the y-coordinate stays the same for the endpoints of the minor axis. And then finally, what about the c each way? So remember, c squared is a squared minus b squared. So we get 16 minus 4, which is square root 12 for c. Well, you could give that an approximate value, but and the calculator will put that to decimal, but actually we want it in exact form. So we want to rewrite that as square root 12 or 2 root 3. And we're going to, again, put it onto that same way with A along the major axis, so it's going to affect the y coordinate of the center only. And we're going to add it and subtract it to sort of a slider, slides a little bit up and a little bit down from the center to mark those points. The last thing we might want is our eccentricity. That value is C over A, and you can just get that as a decimal, about 0.87, which tells me that it's definitely not going to be misconstrued as a circle. It is definitely more elliptical in shape. The closer it is to 1, more elliptical. Closer it is to 0, more circular it appears. All right, and we're going to close today with some multiple choice. You might want to pause it here, kind of give yourself a little exit ticket, and then come back and let me go through it with you and check your work. All right, so hopefully if you've paused it and you've done your work, we're just checking it over, so I'll just slide through. For the first one, it tells me my major axis has a length of 6, and it is a vertical major axis. So I know the bigger number needs to be under the y. So I'm kind of looking at A or D, because those are the two. Well, actually B also has a y that's bigger. So that doesn't tell me a lot right off the bat. But I do know that my major axis is 2A, and 2A is 6, so A is 3 and A squared is 9. So I need a 9, and it needs to be vertically situated. That alone is enough to kind of make our conclusion, I think. But let's just go ahead and finish it up if it weren't multiple choice. How do I figure this out? Well, I'd need to know that the minor is 2B, and B is 2, so B squared is 4. Because it's a vertical major, I know the 9 is going to go under the y, and the 4 is going to go under the x term. We don't know the center. It would have to tell us in this case that it has a center at 0, 0 if we were writing on our own. But since it is multiple choice, I think we can definitely pick it out of the lineup. All right, for number 2, we're asked to find the center, vertices, and foci of the ellipse with the given information. So where do we start? Well, notice the center is definitely 1, 4. You can't argue with that because all the choices are the same. So the next thing we're going to do is decide maybe which way. Do we see the larger denominator is 25? So that indicates to us that our vertices are going to be 5 up and 5 down from the center. So I would kind of start with a sketch here. Moving 5 up from 1, 4, I get 1, 9. Moving 5 down from 1, 4, I get 1, negative 1. So those are my vertices. And I see those vertices in choice B and C. So I've got to go just a step further. The next step is for foci. So if I want to find my foci, I have to find C. And remember how to do that is that Pythagorean-ish relationship where C is a leg and A is the hypotenuse. So keep that in mind. 25 minus 16 gives me 9. So C is actually 3. So if C is 3, I can throw in my foci, up 3 and down 3 from my center. And that would put me at 1, 7. 1, 9. Whoops, wait a minute. Where am I? Yeah, 1, 7 and 1, 1 for my foci. Kind of lost track there for a minute. There's my 1, 1, and here's my 1, 7. So up 3 and down 3 from my center location, and that clarifies it for me to choose the right one. If you want to finish graphing, you can go out 4 each way and then sketch it in. Number 3, I'm given the equation and I need to find the eccentricity. So that's C over A. So I need to find C. Now notice this is the same ellipse we just worked with above, and we already found C, but let me show you that again. We see that C is 3. It's vertically situated. So I get 3 over, now be careful, don't use 3 over 25. It's just that, remember the 25 is A squared. So we just want A, so it's just 3/5, which would give me 0.6. And for the last one, to rewrite in standard form. I mean, this is kind of like that circle problem we talked about earlier where we had to divide everything by, but in this case we don't want to divide by 16, we don't want to divide by 25. We actually want to divide by the 400 because we need it to be equal to 1, so we're going to divide it by the constant. We don't have to complete the square because there are no linear terms here. There's no linear x, there's no linear y, so basically it's in general form, but it's a very simplistic general form because the origin is my center. So just divide everything by 400, reduce down to lowest terms, and you should see your answer as C. All right, excellent work. I hope this helped you today, and good luck with your assignment. Just be sure to let me know if you have any questions.